In this video, we're going to take a look at polygons, and we're going to particularly look at interior and exterior sum formulas. Now, before we do that, let's take a look at listing polygon names. So here's what I would encourage you to do. I would encourage you to pause this real quick and to come up with the names of polygons, as many as you can come up with. So notice here, if you have 3 sides, that's something called a triangle. 4 sides, a quadrilateral. Okay, we're familiar with that. So what would a 5-sided polygon be called, or 6, or 7? See if you can come up with exactly what the correct answer here would be. So let's go through this. Hopefully you've written yours down. So 5 sides, that would be a pentagon, right? Penta meaning 5, pentagon. 6 would be a hexagon. 7, now you could come up with 2 different things here for 7. You could come up with heptagon, H-E-P-T, or septagon. I prefer septagon, but you might see a heptagon with an H instead of an S here. But septagon. 8 is an octagon. 9. Now 9 is a little bit of a strange one. 9 is a nonagon. Okay. A nonagon has 9 sides. It's kind of a unique name, but you are responsible for knowing these names and for knowing what a nonagon or a septagon is. 10 is a decagon. You can think of a decade being 10 years, so a deca is usually linked with 10. So I'm sorry, put decade there, decagon. And then 12 is a do. Sometimes we use that for 2. A dodecagon. Or 2 and 10, dodeca, 2 and 10 would be 12. So there are names for shapes like that have 11 sides or 13 or 31, really almost any number of sides, whole number of sides you can think of, there's probably a name for it. But these are the key ones that you do need to know for sure. The other ones, everything else we end up just calling like an 11agon. Like if we want to talk about a 11-side polygon, we would just call it a 11gon. Okay, or a 34gon or something like that. Now there's one more thing that I do want to talk about here. Hopefully some of you picked up on a pattern here. Notice this. I've got septagon, octagon, nonagon, decagon. What does that sound like? Well, sept sounds like September, October, November, December. Those sound like the months. But here's the question. Why, if septagon means 7, why is it the 9th month? Why is September the 9th month? Why is October the 10th month, not the 8th month, and November and December? Well, hopefully you learned about this in your history class. But remember there was a guy named Julius Caesar. Thought he was big stuff, head of the head of the Roman Empire, and he thought he was so important that he said, you know what this country really needs? It needs another month. They had 10 months at a time where December was the 10th month and November was the 9th month, and it all lined up, and he said, you know what we really need? We need a month named after me. And so he created the month of July. And then along came Augustus Caesar, and Augustus Caesar said, if Julius Caesar got a month, I get a month too. And so then they went from 11 months to 12 months, and we got the month of August. And so the reason that September, October, November, and December are named are based off of numbers, but because of Julius Caesar and Augustus Caesar, we have 2 additional months in our calendar, so now we have 12 months, so they don't actually line up with the numbers. But that is an easier way to help remember nonagon and septagon, that they are linked to the months September and November, and if you can remember that it's just 2 back instead of being the 9th month, it's connected with 7. Anyways, I find that really interesting. That will not be something that you're quizzed on. I just think it's interesting. All right, so let's keep moving forward here. Let's review some vocabulary. So remember a polygon. It's a closed shape with any number of only straight sides. So it only has straight sides, and it can have any number of them. And it's closed, so you can't have, they're non-intersecting, so you can't have like this would not be a polygon because there's an intersection point here. And then something like this would also not be a polygon because it's not closed. Okay, so those are some polygon definitions. There are things called convex polygons and concave polygons. So you also see this with like glasses lenses. There's convex lenses and concave lenses. So convex polygons, notice that the polygon is kind of like what we would expect it to be. The angles inside the polygon, you don't have any like dips into the polygon, whereas look at the concave, you know, I've got, you know, in a sense, a dip in my polygon where it kind of caves in on itself. Okay, so convex, those are going to be your typical polygons, the ones we're going to spend most of our time looking at. But then there's also concave polygons, such as this, where you have these angles, or even just one. You could have a concave polygon that looks something like this. You know, anytime it's going in on itself, that's going to be concave. All right, so let's talk about two more things: interior angles and exterior angles. And these are the formulas we're going to learn about. We'll do interior angles first, and we'll do exterior angles. So interior angles are on the inside. Okay, so like this right here would be an interior angle. This would be an interior angle. Okay, that should not be surprising. And then exterior, you can think about exit or an exterior decorator. Somebody decorates the outside, or an interior decorator. Somebody decorates the inside of a building. At the exterior, let me do this actually in a different color so we don't get confused. So the exterior is like this angle right here. If I were to extend one of the sides, that would be an exterior angle. So interior angles are on the inside, exterior angles are on the outside. So what we're covering today is how do we find the sum of all the angles on the inside, and how do we find the sum of all the angles on the outside. So we're going to start with the interior sum. So the interior angles add up to n minus 2 times 180, where n is the number of sides. Okay? Now let me show you why this is the case. We're going to kind of explore this, talk about this. The actual work for this lesson is quite easy, but I want you to see where this is coming from, help you kind of understand what's happening here. So when we're dealing with interior sum, okay, we know that a triangle has how many degrees? It has 180, right? We know that about all triangles. Now, let's think about the square, or a quadrilateral, is a square here on the screen, and let's think of it as comprised of triangles. If I draw from vertex to vertex a line here, how many triangles do I have? Well, I have 2 triangles, okay? And notice this thing here, okay? Now, you might say, well, wait a second, Mr. Arslan, I can just draw another one, and another one, and another one. Okay, well, yes. Thank you, DJ Khaled. When we're doing it, we can't, if we cross, notice how I've made some triangles, but look, I've got angles all in here. What I'm looking for is to make as many triangles as possible, but not having any intersecting lines here, so that I'm just comprising of triangles, and all the angles of the triangle are also angles of the quadrilateral. So in this case, notice I have 2 triangles, or I have 2 times 180 degrees. Okay, do we see where that's coming from? Let's look at this next one. Let's draw some triangles. So I could draw a triangle here, I could draw a triangle there. I've got 1, 2, 3 triangles, or 3 times 180. That would be the number of degrees inside that polygon. And here I could draw one here, and there, and there. Notice I've got 1, 2, 3, 4, or 4 times 180. Now, if we think about this instead of in terms of numbers of triangles, because say you have a dodecagon, you've got 12 sides, it's not going to be a lot of fun to be trying to draw tons of triangles. Instead of thinking about it that way, let's think about it this way. Let's think about the number of sides and how they relate to the number of triangles we have. So notice here I have 3 sides, and how many triangles? 1 triangle. I've got 4 sides and 2 triangles, 5 sides and 3 triangles, 6 sides and 4 triangles. Or what I can say is the number of triangles is equal to the number of sides minus 2 times 180. So if I want to find the number of angles or the number of degrees in a decagon, 10-sided polygon, I would do 10 sides minus 2. That tells me how many triangles I have times 180. And that would end up coming out to 8 times 180 for 1,440 degrees. That would be a decagon, the number of degrees in a decagon. Okay? So that's where the polygon formula comes from. You do need to know n minus 2 times 180. That is a formula we're going to see a lot in the next week, and it is something that you would be expected to know for like the SOL or any future assessment. All right, so let's find the sum of the interior angles here. So we did one just like this, but we'll use the formula this time. So I've got 5 sides, so 5 minus 2 times 180. And 5 minus 2 times 180, that's 3 times 180, or 540. Okay, so again, very simple. I know we did a lot of time kind of talking about the theory behind it, but the actual problems are not that bad. Let's look at one more here, finding the sum of the interior angles. Notice I got 1, 2, 3, 4, 5, 6, 7 sides. So I'm going to do this is septagon, 7 minus 2 times 180. And when we plug this in, we do want to make sure if we're plugging it into a calculator or Desmos that we're using parentheses, or order of operations, we'll do the 2 times 180 first. So do make sure you use parentheses, and we end up with 900 degrees. Okay, so that's pretty simple, right? So now let's look at the exterior sum. Okay, the interior sum, the angles inside the polygon, is the number of sides minus 2 times 180. However, the sum for the exterior angles of any convex polygon is always 360 degrees. So it doesn't matter if I have 5 sides, 12 sides, 1,000 sides, the exterior angles, and that, again, it's like this saying, if I add up all these angles, or all the way around here, I would get 360 degrees. Now, maybe that's a little surprising, that it's 360 for every single one. Well, let me show you kind of why that is the case. Okay, so here's kind of a graphic. Now look, watch what happens. This polygon is going to expand and collapse, and see if we can see why that's equal to 360 degrees. Notice that at the very tip, when it kind of collapses, as we take that thing smaller and smaller, notice how all these exterior angles end up being the whole way around a circle, or 360 degrees. Now let's try one with less sides. What if I try one that's a hexagon? Notice what happens. It expands, it contracts, and all the way down, it comes down and ends up being 360 degrees. And I could change it to any number of sides I wanted. I could change it up to 12 sides here, but the same thing happens. Notice all those exterior angles stay the same size, and if I shrink it down small enough, they end up going the whole way around a circle. So that's kind of why, just kind of visually why this formula works. I know it's a bit unusual as to the fact that it does work, but it does make our lives really easy. So let's look at 2 problems. What are the sum of the exterior angles? 360. Done. What's the sum of the exterior angles of the 7-sided polygon? 360. Done. Okay, so the 2 big takeaways, well, really 3 big takeaways. 1, you need to know your polygon names. Okay, up through 12, not including 11. 2, you need to know your interior angle sum. So that's n minus 2 times 180. And 3, you need to know that all exterior angles always add up to 360 degrees for convex polygons.